Welcome back. This is the last lecture of this course of lectures, and where we'll discuss two case studies, are longer examples with more details. Both these case studies are connected with the work that I had done in my career. The first study pertains to an inquiry that I received in late 80s from Maharashtra Electricity Supply Company. They were building power plants or extending the power plants in Chandrapur, super thermal power stations. And they were designing 3 chimneys, each 200 meters tall. And they were worried about their elastic properties. What happens to them when the wind blows past them? We know as the wind blows past a circular section, there are vortices that are shed. And these vortices that are shed result in transverse forces on the cylinder, and these transverse forces could result in transverse vibration of the chimney. And if the frequency of this vibration coincides with the natural frequency of the chimney, then the chimney could collapse. And so they wanted me to investigate this problem and see that the natural frequency of the chimney is far away from the frequency of the vortices being shed. The aeroelastic behavior of a tall structure like a tapered cylindrical chimney is governed principally by its inertia and elastic forces, and by the inertial forces of the wind that acts on it. The viscous effects are usually negligible because of a very large value of the Reynolds number involved. Since the chimney can be considered as a smooth cylinder, the vortex shedding from it are somewhat dependent on the Reynolds number. But this dependence is usually small at very large Reynolds number of the order encountered in the practical cases. Further, the platforms and these spiral staircases along the chimney would make the vortex shedding frequency quite independent of the Reynolds number. So therefore, it was quite reasonable to neglect the viscous effects completely. We allowed for different scaling factors for diameters and thickness, and that was required because of the differences in the densities of the prototype and model material and the difficulty of fabricating the very small wall thickness required if the same scaling factor was used. The following scaling factors for the various forces can be obtained. For the inertial forces of the chimney, the scaling factor for the force K1 is K rho C. Rho C is the density of the chimney times the mass of the chimney, which would vary like KL square times KH, and the acceleration K omega square KL for vibratory mode of the chimney, vibrating at a frequency omega. The inertial forces of the air, convective acceleration. K rho A, scale factor of the density of air, rho A for the density of air, KL cubed into kV square by KL, the scale factor for convective acceleration. For the vibratory inertial forces of the air, unsteady inertial forces in the air, K3 is K rho A, KL cubed, which is mass, and K omega square KL, which is acceleration. The elastic forces in the chimney wall, K4 is Ke, K epsilon into cross-sectional area, which will be like KL, KH. H is measured in the thickness direction, and L is the length and the diameter scale. For identical curvature, that is when K radius is KL, K epsilon is 1, so that K4 is like Ke, KL, KH. And the last of all, the viscous damping of the wall material. We use the non-dimensional logarithmic decrement delta, which is 1 over L, ln A naught by An, where A naught and An are the amplitudes at the beginning and end of n cycles of vibrations. Since this is non-dimensional, this itself is a pi number and has to be matched in the prototype and the model. Dynamic similarity requires that the scale factors noted above for each of the force component be the same. This then gives us the following modeling rules. From equality of K2 and K3, that is of the forces relating to the convective acceleration of air and the unsteady acceleration of air, we get K omega KL divided by KV is equal to 1. This is the Struer number. St is equal to omega L by V is invariant. Should be identical both in prototype and the model flows. Next, from the equality of K1 and K2. K1 is the force of vibration in the chimney material, and K2 is the convective acceleration of the air. We get our relation K rho A by K rho C is equal to KH by KL into KL K omega by KV whole squared. This is pertaining to the Struer number. Since KL K omega by KV, the fruit is 1 as already established, and since K rho A is 1, the model fluid is the same as the prototype fluid, both air, because we are testing in the atmospheric air. This means KH into K rho C divided by KL is equal to 1. This is the second modeling rule. So, though we are using the same density of air, by using a different value of KH from KL, we can use K rho C, the density of the chimney material, different in the two cases, the prototype and the model. So, this condition establishes the need for a different value of thickness scaling factor if the model chimney density is different from that of the prototype. Next, the equality of K4 and K2, that is the stress forces within the chimney material and the convective acceleration forces in air, gives you this relation. Since K rho A is 1, same air, This gives you Kv is equal to under root Ke Kh by Kl, and establishes the velocity at which the test is to be conducted. So after we have chosen Kh and Kl and Ke, this gives us the value of Kv. Thus, with the choice of Kl, K rho C and Ke made appropriately, we can first calculate Kh, the wall thickness scaling factor, and then the velocity scale factor Kv. This gives the velocity at which the test should be run to give dynamic similarity. Then this true number equality gives the prediction rule for frequency. So frequency of vibration, the natural frequency of chimney, K omega is Kv divided by Kl. 1 over Kl under root Ke Kh by Kl. This can be used to predict the frequency of the prototype once the model frequency of vibration is measured from the test. To summarize, the process of modeling is to choose appropriate KL. We ended up a value of KL very large because the test section of the wind tunnel available to us was quite small. It was 70 centimeters by 90 centimeters. Then choosing modeling material and obtain K rho C, the density scale factor, and Ke, the elasticity scale factor. Then obtain Kh from the modeling rule equation 3 above, and then obtain the velocity scale factor and the velocity to run the model test. If we do this, this ensures dynamic similarity if the log decrement is also identical. Then from the measured values, following the rules can be used to predict prototype quantities. K omega, K amplitude would be like Kl, K epsilon is 1, and K sigma is like Ke. Keeping in view the dimension of the test section in one experiment, the length scale factor Kl equal to 450 was used. This would result in a wall thickness less than 1 millimeter. To facilitate fabrication of the model, it was decided to use structural grade glass fiber reinforced plastic. We chose Araldite LY 556 with hardener HY 951. The average density whose composite with the glass fiber cloth was measured as 1720 kilogram per meter cube. Since the average density of RCC can be taken as 2500 kilogram per meter cube, the resulting scale factor for the chimney material density was 1.45. Then using equation 3 above, the wall thickness scaling factor was obtained as 310, quite a bit smaller than 450 for the length and diameter. This shows the dimensional sketch of the model chimney, which is not drawn to scale because the length is quite large. KL is equal to 450, KH is equal to 310. The dimensions of the model chimney shell are as shown in the figure. The actual prototype chimney had a firebrick lining. How to model that? It was assumed that the firebrick lining of the chimney contributed only to the mass and no stiffness and no damping. Therefore, it was modeled by a dummy mass. We used a rubber lining of the model stuck in the inside of the erudite fiberglass composite chimney. It was stuck loosely so that it did not contribute to any stiffness or damping, but only to the mass, representing the mass of the fire brick lining in the prototype chimney. The mass per unit area of the fire brick lining in the prototype is approximately 321 kilogram per meter square. So for the model, it should be 321 divided by 450 or 0.715 kilogram per meter square. An appropriate rubber lining was bonded to the shell using Fevicol. The mean elasticity E of RCC is 35.3 gigapascal, while that of the RPF composite used is 4.5 gigapascal. This implies a scale factor for E as 7.84. The required modeling velocity scale factor then is obtained as 2.32. A very reasonable scale factor for velocity, which could be easily implemented in the wind tunnel that we had. The prediction rules are then obtained as K omega is Kv divided by Kl, which is 0.0051. K amplitude is like Kl or 450. K strain is like 1 and K sigma is like 7.84. This summarizes the various scale factors for the model and for the results. 3 kinds of tests were conducted. In the first series of tests, the chimney model was mounted rigidly on a wind tunnel floor and was subjected to properly sheared wind profile with no terrain modeling upstream of the tunnel. The actual prototype chimneys were to have buildings to the north of the chimneys. So, when we use no terrain modeling upstream of the tunnel, this represents the condition when wind blows from any direction but the north. The strain and static deflection of the chimney were measured by 4 1.5 millimeter into 3 millimeter wire strain gauges mounted near the base of the chimney at 4 locations 90 degrees apart. The strain gauges were energized by V-shaped strain indicator and signal displays on Tektronix type oscilloscope. The dynamic displacement tip was picked up by B&K type 4374 accelerometer energized by a charge amplifier B&K type 2635 and the dynamic signal displayed on this oscilloscope. The logarithmic decrement on the model was found by shaking the model and taking a Polaroid photograph of the decay of the strain signals on the CRO. Careful measurement gave a value of delta is equal to 0.18, the logarithmic decrement of vibrations, which falls very much within the minimum and maximum limits for the concrete shell. Since this was a modeling requirement, this was met. So now, after proving that the requirement for invariance of logarithmic decrement was met, a second series of experiment was conducted. In this properly scaled block representing the various structural upwind of the chimney for the northerly wind was pasted on the floorboard, and inline tip deflection and strain, both static and dynamic, were recorded, as also the lateral strain and tip deflection amplitude. This represents the condition with wind blowing across the powerhouse and other structures to the north of the chimney. The third series of experiments explored the effects due to wake buffeting. For this, 3 chimneys model were mounted inline in the tunnel with the air blowing along the centers. The lateral vibration of the downstream chimneys was picked up by strain gauges and accelerometers. All these tests were repeated for a chimney without the inner lining, representing the condition when the chimney shell has been constructed, but the brick lining work has not yet been assembled. One of the results looked like this. Wind velocity on this scale, model wind velocity was 2.33 times higher because kV was 2.33. So this is wind velocity of the prototype on this scale. Same graph, wind velocity for the model. Tip deflection of the model here and in millimeter, and this gives you the strain of the prototype and strain of the model. The results were well within what was acceptable. The next is a complex modeling exercise in which the mechanism of human voicing was explored. The human voicing apparatus consists of lungs which exhale air through trachea across the glottis. The glottis vibrate and produce sound. So functional components are lungs and diaphragm, which push air past the glottis into pharynx, and which is divided into passing through the oral cavity or through the nasal cavity. These glottis, the vocal cords, vibrate when the flow goes past them. What makes them vibrate? What is the mechanism? It was expected to be aerodynamic in nature, is that the pressure forces which oscillates make these larynx oscillate. So if this is the medial section to the larynx, the air goes around this. This is towards the mouth. This is from the lungs. And as the air flows this, these two vocal cords, which are mass and which are elastic, vibrate. Why do they vibrate? If there's a mass spring dashpot system, the equation of motion can be written as mx double dot is equal to minus cx dot minus k, where k is the spring constant, c is the damping coefficient, and m is the mass. X is the displacement of the mass. In a vocal fold, as the wind passes through this, the energy is fed into the vocal folds. So if we're writing the equation of motion of the vocal folds, this C should be negative. That is the damping, that is the result of aerodynamic forces. That is the force component should be in phase with the velocity, so that the C is negative and we get energy fed into this vibrating system. So, if we make a model, let us represent this to be the center line of the glottis. So, there is only one vocal fold that we are shown. We assume a simple model which is tapered at an angle theta or width b. So, when this is moving up, there should be a force here which is upward. And when it is moving down, there should be force which is downward. The force is applied by the pressure of air. So, the pressure on this face of a model vocal cord should be negative when it is moving up and should be positive when it is moving down. This results in feeding energy into the system. The mechanism that we suspected at the beginning of the study was something like this. It was assumed that this edge of the vocal fold is rounded, which it really is if you look at the vocal folds. And this roundness has something to do with why the energy was fed in. The suspected mechanism was that as this vocal fold vibrates, the air coming in separates at this edge. It comes out as a jet. But the point of separation oscillates around this curved, rounded edge of the vocal fold. When the vocal fold is moving up, the point of separation moves down so that the separation is a little below the top of the aerofoil. Since the velocity of the flow here, in the absence of viscosity, is related to the pressure there, and so this velocity is constant, quite independent of the location of the vocal fold or the velocity. And since this area is larger, this velocity is same, this area here is smaller. So the velocity is larger and the pressure here is smaller. And so as the pressure on this is smaller, this means that there is a force upward. When this is moving up, there is a force upward, the right direction of force. Larger area, larger velocity and lower pressure. But when this is moving down, the point of separation moves back to here. Now this smaller area, smaller velocity and higher pressure. So while it's moving down, there is a higher pressure and this tends to push it back. We started our investigation with this hypothesis. A model was constructed, a plexiglass in which we use dummy springs. This represents the vocal fold mounted on a brass reed And this provided a springiness to this. As it moved up and down, this brass reed bent and created stresses. Strain gauges at this location picked up the vibrations. We could adjust the opening by using this micrometer screw gauge. The wind moved in that direction, and the results steadied. The signal from the strain gauges was sent to a CRO, and pictures taken. This is how the vibration grew when we started from rest. From this, we could determine the logarithmic increment rate, delta, as discussed in the previous case study. And from this, we could determine the rate at which the energy was fed. After doing lot of work with this setup, it was concluded that not enough energy was being fed, that this mechanism was not explaining the mechanism for the actual human vocal cords, or even for this. Where is that energy coming from? So, with lack of any leads, ISRO decided to do some model test with a large model in a water tunnel. A 1/10 scale model, that is 10 times the size of the vocal cords, was constructed. It was driven by a cam driver so that it moved up and down. There was mechanism to inject dye at this, so that while the experiment ran, we could see the movement of the separation point by noting down where the dye streak was separating from this model vocal fold. The inertial forces in the water, scale factor for that is K rho, KL square, KV square. The unsteady force scale factor is K rho, KL4, K omega squared. And so this gives you this total number with KL 1/10 and the KF of 3/110. For human vocal cords, the frequency was taken 110, and for this model was running at a frequency of 3 vibrations per second. So that gives you a KV of 1/366. The velocity in the prototype is of the order of 100 meters per second. So therefore, the velocity of the model was 2.7 centimeters per second. We ran the test at that scale. And when the tests were run at that scale, something interesting was seen. Surely there was shifting of the separation point at this rounded edge. But this was very minor. Very interesting thing was seen here, that the level of the fluid in the tank upstream was fluctuating at the same frequency and in phase with the motion of the cam driver. When it was moving up, the level was going up. When it was moving down, the level was going down. In fact, this was the eureka moment. So it is the capacitance of this upstream system which is responsible for producing the force in the right phase, in the correct phase, to feed energy to the vibrating system. Going back to the experiments that we had. In the same model as before, we stuck in a microscope here to measure the fluctuations of pressure. And we found out that the pressure fluctuation were in the same direction as required for feeding in energy. We constructed an analytical model and we determined that this does feed the energy. We did experiments on an earlier air model and we found out the P1 divided by A1 versus velocity. The analytical model fitted very well. The dots are the major points. The line is the calculated line. So this does explain the phenomena. How does it translate to human vocal cords? We looked at the model of the lungs. This is throat. Distance from the throat in centimeters. You see, the lungs are a series of branching tubes. Basic trachea, then the first generation, then the second generation, up to about 25 generations. And they measure the total of the area for each generation. This is what the graph looks like. So when the diaphragm pushes air through the lungs, it is as if we are feeding air to the larynx through a tube which is open at this end. So this is what the model is. This is the trachea and the lungs. This is the length, effective length of that tube that we found out in this model for about 29 centimeters. So this is how, now this is a reactance model, not a capacitance model. This is a tube. Air flows past this. And then if this sets into vibration, then the energy is fed into this and for particular frequencies, not all frequencies. This could explain the mechanism. There was more work done, which I'm not presenting here, because this permitted voicing only in a certain range of frequency. So to cover the whole range of frequency, we had to construct what we call a two-mass model. And that two-mass model could explain the energy feed into the vocal cords at all frequencies. Thank you.